uh, mute yourself, and if you have a question, unmute and ask a question. If you are asking a question, it's good if you share your video. All right. Um, so today we're happy to have Tom Hartman giving us a virtual talk from Cornell University about islands in black holes and cosmology. Thanks so much, Tom. Go ahead.
All right, thanks a lot for having me. So this is gonna be sort of a two-part talk. And what I thought I would do is the following plan. So part one will be about islands in black holes. And my goal here is to give a broad overview of the developments on the black hole information paradox over the last 2 years. I think there's a pretty good chance that you've seen, some of you at least, many of you have seen talks about this, maybe you've had seminars about it. But I'm gonna do that first to set the stage. And if you haven't seen it, great. If you have seen it, then I hope you'll take this as an opportunity to stop me and ask questions. We can discuss any parts of it. That'll be pretty broad. In part two, I'm gonna ask the question, to what extent can we apply these ideas to cosmology? And there's a question mark on part two because I don't think we really know the answer to this question yet. There are some important similarities between cosmology and black holes. They both have horizons, for example. And some of these ideas do appear to show up in cosmology. I'll give some examples where that is the case, but I think we have yet to really understand the full picture for cosmology. So that's the plan. And please do just stop me with questions, just shout them out at any point. Okay, so black holes. The recent work on black holes is focused on reproducing the Page curve. The Page curve is the plot of fine-grained entropy of black hole radiation. So this is Hawking's calculation. And what we see on this curve is the radiation is thermal. So as more radiation is emitted, the entropy of the radiation goes up, up, up. And eventually the black hole is gone and the entropy saturates at some finite value. Now, this is fine-grained entropy. It's a microscopic entropy minus trace of rho log rho. And that has to be 0 in a pure state. So that's the paradox, is that this should have come back down to 0 because the radiation should be pure, but it didn't. We can make that sharper by comparing that to the area of the black hole that's evaporating. So the area, so the black hole is emitting Hawking radiation, so it's shrinking. Its black hole is getting smaller and eventually disappears. And the point here is that we see the information paradox as soon as these two lines cross. Because the entropy of Hawking radiation comes from entanglement. It's really an entanglement entropy that is measuring how much entanglement there is between the quantum fields outside the black hole and the quantum fields inside the black hole. That's where that entropy is coming from. And the amount of entanglement entropy that you can create by entangling is bounded by the amount of stuff that you're entangling with. Okay, in this case, you're entangling with the black hole. If you believe that the black hole has entropy area over 4, then that's the most entanglement entropy you can create by entangling with the black hole. So as soon as these two lines cross, you have a conflict with unitarity. What Page argued from some simple quantum information point of view is that if black holes evaporate unitarily, then what they should do is follow the dotted line. That is, the entropy should, at early time, should increase along the lines of Hawking's, exactly following Hawking's calculation. Then, right when you get to the point where there's a paradox, the fine-grained entropy should suddenly turn over and come back down towards 0, following the area of the black hole. So this is what it should do in a unitary theory, compared to what it seems to do according to Hawking's calculation is the red line. So a point of view that a different point of view that we can take here is by thinking about the Beckenstein area bound. And this is going to be important for motivating the cosmology discussion later. So let me just make that point now, is that we can rephrase this in terms of the interior Hawking partners. That is, you have some partner particles inside the black hole that are entangled with the Hawking radiation. The entropy of those quantum fields in the interior is equal to the entropy of the Hawking radiation, because the quantum fields are pure on a Cauchy slice. So the paradox appears when the two lines cross, which we can phrase in this way. The two lines cross is the statement that the quantum fields inside the black hole have entropy bigger than the area of the black hole over 4. This inequality is something famous because this is what I call a Beckenstein area bound. It goes by various names. Sometimes it's called the holographic bound. And this bound is being violated. So the Beckenstein bound says that the entropy of some quantum fields is bounded by area over 4. Now the true Beckenstein bound is for static black holes. So that's why there's no reason, it's not a violation of Beckenstein's original bound, which was for a static case. This is an evaporating black hole. But it's violating this Beckenstein-like bound or holographic bound. And so the point I'm trying to make is that when you have that the existence of these paradoxes is related to violations of the Beckenstein-like bound. Okay, so why is this? So when we call this a paradox, we need to be a bit careful about what we mean by that, because Hawking's calculation is not exact. What Hawking showed is that the density matrix of the radiation is thermal, but of course he's working in the low energy theory, and there are corrections to this statement. There are perturbative corrections, and there are potentially non-perturbative e⁻s corrections, where s is the entropy of the black hole. Now, this is sort of a loophole. This is really a loophole in Hawking's argument, because if there are e⁻s, these tiny non-perturbative corrections to each matrix element of the density matrix of radiation, rho sub r, then even those very tiny corrections are big enough to change the entropy at leading order. Because when you calculate an entropy, in this case, the entropy of the radiation, you're summing up e⁻s terms. So if you put these little e⁻s's in each term, you can get enough to make a big difference in the calculation of the entropy. Okay, so there's sort of this loophole coming from non-perturbative, potential non-perturbative physics in Hawking's argument. So why call it a paradox then? Well, 2 reasons. First of all, local corrections don't help. That is, there's no way that you can just add some even though these are tiny effects, they have to be non-local. And that's something that you can prove very directly. Then the question is, where could these non-local effects, where could these non-perturbative, non-local effects be coming from in quantum gravity? There was no mechanism to produce terms like this or to understand where they could possibly come from. So that was the paradox. The recent developments over the last 2 years have led to a new understanding of this. The summary is that non-perturbative effects in the Euclidean gravitational path integral do contribute and are calculable. You can calculate their contribution to the entropy, and once you include these non-perturbative effects, you reproduce the unitary page curve. Now, this is not a complete solution of the puzzle. It doesn't really tell us in detail where what the e⁻s effects are for the individual matrix elements, but it gives us a better handle on calculating the entropy.
Quick question.
Yeah.
So here we are sort of saying that the Euclidean path integral is sort of a non-perturbative definition of the theory if we're taking the non-perturbative corrections seriously. Is that?
Well, it's not a it's not a UV complete. It's certainly not supposed to be a UV complete definition of the theory, but that's a different question compared to non-perturbative effects. So these are non-perturbative effects that are similar to the Hawking-Page transition. The Hawking-Page transition is a transition between two saddle points. So that is a non-perturbative effect, but it's still something that you can see in the low energy theory. It's not a UV. There can be non-perturbative effects that are nonetheless captured by the infrared.
But is it fair to say that this goes beyond the standard formalism of effective field theories?
Well, I don't think it, well, it certainly goes beyond the standard formalism of effective field theory in QFT. I don't think it really goes beyond the standard formalism that we apply to gravity. It is pretty standard in gravity to sum over saddle points and include non-perturbative effects like this. We just didn't know about these particular saddle points before. The Hawking-Page transition being probably the most famous example.
Thanks so much.
Okay, other questions at this point?
Actually, one more question. Are you going to comment on this? You mentioned this one way to think about the paradox is to say that the interior entropy is larger than area over 4G, and this is related to Beckenstein bound.
Yeah.
There is a version of that that was suggested using relative entropy by Cassini and Maldacena and friends. Are you going to comment on that, or?
I wasn't going to comment on the relationship. It's a slightly different Beckenstein bound. So that Beckenstein bound is the one that says entropy is less than energy. And this one that I'm calling the Beckenstein area bound says that entropy is less than area. So it's, they're related for a black hole in equilibrium. These two are related, but it's a slightly different bound that's going in here.
Thanks.
Okay, so what I'm going to spend the rest of part one on is explaining these recent developments, and it starts with a formula called the island formula for the entropy of Hawking radiation. So what I'm going to do is, so the history here is that these ideas came from holographic entanglement entropy and led to this conjecture, the island formula. And then that conjecture was later derived from the Euclidean path integral. So I'm going to start by telling you the formula. Then I'll sketch for you the derivation from the Euclidean path integral. And then we'll go from there. Okay, so here's the formula. This is the Penrose diagram of an evaporating black hole. The radiation is collected out here in the region rad. So we pick a region and we want to calculate, our goal is to calculate the von Neumann entropy of this region rad. And the formula that was conjectured looks like this. Here's what it says. It says that first you should define an island. So an island is a region inside the black hole, given by this blue segment here. Then you should calculate the generalized entropy of the island union the radiation. Okay, so this has two terms. It has an area term from the island, and then it has an entanglement, a matter entanglement term, which is the von Neumann entropy of island union rad. So this is some generalized entropy. And finally, you should extremize over the choice of island. Okay, so the island is something that you postulate, but then you don't get to say where it is. That's determined dynamically. And so you should extremize this generalized entropy. And finally, if there are multiple extrema, you should pick the one with minimal entropy. Now, one of these extrema is always the nothing island. So you can always just pick the island to be the nothing region. There is no island. So that's always one possibility. And so really how this works in practice is you look for a non-trivial island and then you compare the non-trivial island to the nothing island and ask which one is dominant, that is, which one has minimal entropy. Now, as I described earlier, when Hawking radiation is produced, it's produced in sort of well, roughly speaking, entangled pairs are being produced. And one of those particles is headed out towards infinity and lands in this region rad. The entangled partner stays inside the black hole, and so can land in this island here. And what you find is that at late times, the island is there is an island, this formula has an extremum, and the island is approximately the full interior of the black hole. The crucial fact is that therefore the Hawking radiation does not contribute to the second term, because here in this formula, this entropy term is the entropy of the union of these two regions. And if you just had access to one of them, it would have a huge entropy. That would be the huge entropy of Hawking. But if you have access to both of them, then this term is actually zero or very nearly zero, because if you have access to both of the entangled partners, then that's pure and doesn't contribute to the entropy. What that means is that this formula is just given by the area term. So this formula gives 1/4 of the horizon area at late times. And first of all, that exactly agrees with Page's prediction for the unitary entropy curve. And secondly, it goes to zero, of course, as the black hole evaporates, and so is compatible with unitarity. Okay, so this is a formula that was conjectured on the basis of comparisons to holography and ADS-CFT, and we're going to derive it in a few minutes. But before we do that, I want to comment on the interpretation, because this formula is not just a formula for the entropy. That's its first role in life is to give you a formula for the entropy. But it's something deeper than that, because what it really gives us is it tells us how to think about the inside of the black hole. And this idea comes from ADS-CFT, where it's called Entanglement, Wedge, Reconstruction. The statement is that the island is actually encoded in the radiation in a sense that's similar to holographic duality. It's not holographic in the sense of reducing the number of space-time dimensions. Like if this is a d-dimensional black hole, then the radiation, of course, is also d-dimensional. It's not reducing the number of dimensions. But it's similar to holography because the island region is a region where you're inside a black hole. Gravity is very important. The radiation region is a region where gravity is not important, or at least gravity is weak. So you can treat gravity just you can treat the graviton just as another quantum field. So really out here you have quantum field theory, and in the island you truly have quantum gravity. So in that sense, it's like holographic duality, that you're taking a state in quantum gravity and encoding it in a density matrix or a state of some non-gravitational system. Encoded means that operators in the island, like some field operator phi of x here deep inside the black hole, can be written as an operator in the radiation, just using the A's and A daggers of the radiation modes in principle. Given the entropy formula, this is almost a theorem in quantum information. Understanding what this statement means is very tricky. This is something that Nima has worked on, and there's a whole lot more that can be said about it. But let me just leave it at that and say that this is something we strongly suspect is true. The decoding map is very complicated, but there should be some way in principle of decoding the island into the radiation. So it's really telling us not just how to calculate the entropy, but it's telling us that there's something like a duality where the Hawking radiation gives us a handle on the meaning of quantum gravity inside the black hole.
Good question.
Yeah.
So are you imagining that the boundary of rad is on the horizon?
No, the boundary of rad should be far enough away from the black hole that gravity is not very important. So in explicit calculations, we usually put it all the way on Scry plus. If we're doing this in flat space, we could put this all the way up on Scry plus. But I think it's sufficient to put it, say, 100 Schwarzschild radii outside the black hole. So
Can you go back to your formula then?
Yeah.
So now with this, at lake times, the island becomes the whole interior.
Yeah.
And the SQFT island union rad is still order 1 over g Newton, right?
Sorry, SQFT?
Yeah.
Well, it's order, the order 1 over g Newton part essentially goes away.
Why actually? Because this is still quantum field theory. There's a finite region of space. And the idea is that this entanglement entropy is divergent and divergence is regulated by g Newton. Why does it go away?
You're talking about the infinity from the boundary of the rad region?
Yes.
Good. That term is there. You're right, but that term is time independent. So that doesn't affect anything in this procedure. That'll just come along as an infinite constant.
I see. So somehow that term is renormalized or is irrelevant for our discussion, I guess.
We could keep it. It doesn't hurt anything. You could just think of this second term as having an infinity in it that's proportional to the area of rad, and it just doesn't hurt anything. It's a physical contribution that really is there, and we keep it.
Thanks so much.
And the page curve that I've been plotting has been shifted by infinity so that I can fit it on the page, but it's just a constant.
Yeah, that's exactly what I was asking. Thanks so much.
Yeah. Okay. Are there other questions about the island before I go on to their derivation? I imagine this may be review for many of you. Is that, if that's not true, if you want more details, want me to go slower, we can pause at any point. Just jump in with questions. But I am trying to make it self-contained.
Are you gonna say something about the decoding map?
No, I'm not going to say anything else about the decoding map. I think it's very interesting, but I won't go into it.
Thanks.
Okay, so as I said, this formula was postulated on the basis of holographic duality and wanting to get a unitary answer. And now I'm going to tell you how it's derived from Euclidean path integrals. The short version is that there are new type of saddles that contribute to the gravitational path integral called replica wormholes. And when you include these saddle points in the path integral, they give you a derivation of the island formula and therefore of the unitary page curve. So as suggested by the name replica wormholes, these are going to be calculated using the replica trick. So our goal is to calculate the von Neumann entropy of the radiation, which is this minus trace of rho log rho. Logs are hard to calculate using a path integral, so the replica method gives us a way of dealing with that. We replace the log by a trace of rho to the n. If we can do this for all n and analytically continue to n near 1, then we'll have ourselves a formula for the log by taking this derivative. So that's the essence of the replica method, which has been applied to all sorts of different systems. Here we're going to apply it to the gravitational path integral. Here's the basic idea. And my plan is actually to only tell you the basic idea and then to go on to cosmology so that I can talk about those recent results. But I have some extra slides on more details on this basic idea if you want me to go into that. So here's the idea. When you're looking at when you use the replica method, you're looking now at multiple copies of the black hole. Here's a case with n equals 3. So say you want to calculate the n equals 3 replica partition function, trace of rho cubed. Then you have three identical copies of the black hole and 3 identical copies of the radiation region. And you want to calculate some path integral involving these 3 black holes. The idea is that when you calculate this path integral, there are saddle points where wormholes appear connecting the black hole interiors. I'm drawing this as a Lorentzian picture, but this is really just a cartoon. These are complex saddle points. They're complex spacetimes that so you think of them as being similar to instantons in that they're space-time configurations that contribute to the path integral. And you can find these saddle points exactly in some simple examples. More generally, you can show the following. You can show that these saddle points in the limit n goes to 1 do exist, and that the wormhole mouth, that is these regions where they connect onto these blue regions where the wormholes connect onto the black hole, those wormhole mouths become the island that we talked about a minute ago in the formula for the entropy. Furthermore, you can calculate the action of these wormholes. That's complicated because this is not just gravity, this is gravity plus matter, and the matter term is important. So when I say you can calculate the action, I really mean the effective action of the quantum corrected matter effective action together with the gravitational contribution. But you can do that calculation and you can calculate the action, evaluate it on the saddle point, and when the dust clears, you get exactly the island formula for the entropy. So what was originally a conjecture is really just a property of gravitational path integrals. That's a basic idea. I have some more pictures which I can explain, but I'm going to skip that unless people want me to get into it. So, yes.
I have a question. Is there, so you said there's a Euclidean picture, and there have been attempts to make sense of this as in the Lorentzian signature. Are there criticisms? There are criticisms, but do you have a summary of why the story is more complicated than one would easily naively say that the Lorentzian picture works?
Well, it depends what you mean by the Lorentzian picture. So there's something that we can do, which is to talk about Schwinger-Keldysh type path integrals that are prepared in Euclidean and then evolved in Lorentzian. Okay, that's a little more complicated, but that makes perfect sense. That I'm calling that a Euclidean path integral because even though it has a Lorentzian piece, it's on the same sort of intellectual footing as the Euclidean path integral. Okay, so Schwinger-Keldysh is no problem, and that's why you can use this formalism to talk about evaporating black holes, which that's not a concept that makes sense in Euclidean, but you can apply this formalism by doing Schwinger-Keldysh contours. Now, there's another criticism of this approach, which is that it doesn't really tell you what it doesn't really tell you what's happening in Lorentzian signature, in the sense that in Lorentzian signature, we think that there should be, well, there should be, if this is unitary, there should be an evolution operator, like an S matrix, where I give you the initial state, and then there's some evolution operator that tells you the final state. And using these Euclidean or Schwinger-Keldysh methods do not give you that evolution operator. And that's the operator that would really tell you what's happening in the sense of like you have an initial state that evolves under the Hamiltonian to a final state. So that criticism I certainly agree with. The point is that this Euclidean method gives you a trick for calculating the entropy without knowing the time evolution of the state.
Can I ask something? Because in the usual quantum field theory or even quantum mechanics, an instanton represents tunneling between two configurations. Can you see this as tunneling in some way between two configurations? Although you don't know the exact evolution, you know the initial one minimum, you tunnel to the other, and the instanton is some saddle point that goes between the two. But here is something like that.
Yeah, you can set it up that there's a way of slicing the path integral where you can put it into that language. Yeah, it's just another contribution to the Euclidean tunneling calculation.
But tunneling between what? I don't know here.
Let's see. Well, I think one way of thinking about it is that it's that tunneling calculation is just a transition amplitude between two states. And well, I was going to say it's like a transition amplitude between the initial state and the final state, but that's not quite right because, as I said, we don't really know that transition amplitude in this case. It's more, you can sort of think of it as some contribution to that transition amplitude that's then being summed over initial and final states in order to turn it into an entropy calculation. But I don't think I have it's not a precise mapping to the way we think about instantons.
Okay, thank you. Yeah.
Okay, so now if you go back to the page curve, the point is that if you look at the early time, if you look at the black hole at early times, then the disconnected saddle point dominates the path integral. That's what I call the Hawking saddle here. So that is, if we have multiple copies of the black hole, then the saddle point that dominates the path integral is just the obvious one, where you take n copies of the black hole saddle point. But when you look and do these calculations at late times, there's an exchange of dominance between these two contributions to the path integral. And at late times, it's the connected wormhole topology that dominates the path integral. You can tell already by the formulas on this page why they exchange dominance. It's because when you calculate a replica partition function, it's suppressed as e to the minus entropy. So if you look at this Hawking saddle, then as a function of time, this S Hawking is the entropy of the Hawking radiation. Okay, so as we go to late times, the entropy of the Hawking radiation is getting large. So as that entropy gets large, the saddle point that calculates it becomes exponentially suppressed. And meanwhile, you have this other term over here, which is exponentially small, but constant in time. So that's how they're able to exchange dominance. It's the Hawking saddle starts out big, but then it becomes exponentially suppressed as a function of time. The wormhole saddle, it starts out small, but it stays constant and eventually it dominates.
Actually, Tom, one
Yeah.
little about what you just said. Can you go back to?
Yeah.
So this has confused me. So what the argument you just used is perfectly sensible when you're talking about Rennies, right? N equal 2, N equal 3, N equal whatever.
Uh-huh.
But for entanglement, supposedly we're going to take a limit of n going to 1, and there's an order of limits issue. You first take, Is that something that is understood, or like this order of limits or not?
That's a good question. I guess it's not understood by me. I mean, okay, so the order of limits, I think you're talking about G Newton to 0 versus n to 1.
Yeah.
I guess I don't understand it, but I haven't really thought about it. It might be understood. The same thing happens in holographic entanglement. And I guess my perspective on this is that the analytic continuation in n is not a mathematically, that's not something mathematicians will be happy with. I'm happy if it gives a reasonable answer. If we write down a reasonable analytic continuation and get a physically reasonable answer, then I'm happy with it. But I agree that's something we could worry about. I'm not sure that it's been totally understood.
The reason I comment on this is that this is not too, if you try to make sense of this in finite quantum systems, you realize that this is sort of related to that statement you're making. If you get the density matrix, if you're off by exponentially small corrections in a density matrix, then your entropy, your von Neumann entropy could be really off. It's related to that.
Yes, and I think another, well, I'm not sure whether the crucial thing is that. There's another issue here, which is that at very large little n, like at very large replica number, I'm not sure this calculation is really controlled, especially on the complex plane. So I don't think we really trust the gravitation. So we could ask if we could use the gravitational path integral to calculate the full spectrum of the modular Hamiltonian by calculating all these Rennies. And I don't think that should be possible. That should be something that only string theory knows, or that we need the UV completion to calculate. So that's some issue on the n plane, maybe as n goes to infinity or something. And I don't think that's understood either.
Thanks so much.
Okay. And that's the end of part one. So let me pause here and see if there are questions about the situation with black holes, and then we'll go to cosmology. Okay, part two, cosmology.
Sorry, may I ask a naive question?
Sure.
So the slide one before, yeah, this one. Is it correct to, I don't know, maybe this is naive, but is it correct to say that this is like, first you have pure states going to mixed states and somehow it's purified, and this purification comes from degrees of freedom in islands? Or it's different?
Well, it's a bit like that, but the important thing is that we're not including the island by hand. Like, of course, if you have a mixed system and you purify it, now you have a pure system. There would be nothing surprising about that.
Right.
What's surprising here is that you just do the gravitational path integral. You don't put in the purification by hand. You just do the gravitational path integral, and it tells you that the purifying system, the island, will get included automatically. It's like it knows that it needs to include the island. You don't put it in by hand. It puts it in for you and makes it pure. So that's the difference between what's happening here and what would happen if you just purified it by hand.
Yeah. Okay, I see. So total degrees of freedom shouldn't change, right?
Yeah. Really. That's right. Yeah.
Okay.
The only degrees of freedom here are really the ones in the radiation, and the island is acting as sort of an auxiliary system that's encoded in the radiation and therefore sort of self-purifying.
Yeah. Okay. I see. Thank you.
Okay. Other questions before I go on?
Actually, you mentioned that this extremization over the islands is a dynamical thing. So are you referring to the fact that if you did the Lucas-Maldacena replica trick, you will find this extrema over islands? Is that
Yeah, that's right. That's right.
Okay. Thank you.
Okay, cosmology. Quick summary. Yes, there can be islands, but their interpretation is unclear. Some words of motivation. Well, the way this project started was to ask, other than evaporating black holes, when else do islands appear? Are there other situations? They seem to be very important for interpreting quantum gravity near black holes. What about other situations? Entanglement seems to be, or certainly is key in making an island appear. But then you could ask, well, can I engineer an island? For example, if I prepare some EPR pairs in my lab, now I have a bunch of entangled pairs. Can I send half of my entangled pairs out to Alpha Centauri and do something clever to make an island appear? That would be bizarre and probably inconsistent because it just feels too non-local. It seems that we shouldn't be able to do that. And in fact, I'm gonna prove one thing. I'm gonna prove now is that you can't do that by deriving some conditions on when you can have islands and when you can't, and then applying those to cosmology. Now, in particular, cosmology has lots of entropy, so we could ask if that is the right kind of entropy or enough entropy in order to produce islands, and then look at various cases. So that's what we're going to do. And I'm going to start by discussing some general conditions for when islands can possibly appear. The Island Hunter's Guide. Okay, so the question I want to ask is this. When can a region I be an island? For some region R. That is, I don't want to think about region R, which is like the radiation. this part, in this part, we're really focusing on the island itself, the part that's inside the black hole. And I want to know, is there some way we could tell that the inside of a black hole is going to be an island without ever even talking about the radiation? So that's what we're going to test. So to define these conditions, I need some terminology. Classically, a region is called normal. If under null deformations, it acts normally. And what I mean by that is that outward null deformations increase the area of the surface, area of the region. Inward null deformations decrease the area of the region. That's called normal. A region is called quantum normal if this same inequalities are true, not for the area, but for the generalized entropy. That is the area plus the entanglement entropy of quantum fields. Okay, so that's called quantum normal. And now I can give you the island hunter's guide. So an island must satisfy 3 necessary conditions. First of all, I violates the Beckenstein area bound. I'm gonna come back and give the derivation of that in a minute. Second of all, I has to be quantum normal. And the third condition is that the region surrounding I is also quantum normal. These 3 conditions are very strong and in practice are enough to find islands in all the examples that I know of. So checking these conditions, it turns out, is much easier than applying the island formula. So this is going to give us sort of an easy way to look for islands in various situations when the direct calculation would be much more difficult. I want to give a derivation of condition 1 to give you some flavor for how these arguments work. So the statement of condition 1 is that the Beckenstein area bound must be violated. That is, the entropy of fields in the island must be bigger than area over 4. There turns out subleading terms here, which I'll explain. Now, all of the subtlety in this inequality is dealing with divergences. Okay, so what I really mean by this inequality is that the left-hand side is the finite part of the von Neumann entropy of the fields in region I. The right-hand side is measured in the usual way with the renormalized Newton's constant. Recall that generalized entropy is UV finite. That is, if you take the generalized entropy of a region, which is the area plus the entropy, the divergences cancel. And if you trace that back into this Beckenstein formula, it seems to give you something that's nonsense, that's just completely trivial, because the divergences of the von Neumann entropy, so the von Neumann entropy has a plus infinity UV divergence, and the area term has a minus infinity UV divergence. So if we're not careful about the divergences in this formula, we're just going to be saying that infinity is greater than minus infinity, which doesn't get us very far. Okay. So we have to be careful about these divergences. And that's why the derivation is a little bit subtle. So here's the derivation. The inequality that we want to impose is to say that the entropy with an island is less than the entropy with no island. That way the island will dominate and there can be a real island. If you just write down the island formula for these 2 entropies and reshuffle terms a little bit, you can rewrite it in a way that might be more appealing to a quantum information person as the inequality that the mutual information, sorry, I have a typo here. This is supposed to say the mutual information of I comma R. This is the mutual information of I with R. Has to be greater than the generalized entropy of I. The term on the left is a quantum field theory term. The term on the right is both field theory and an area term. That's just a reshuffling of the inequality. Now we can use strong sub-additivity, which says that the mutual information So I've defined now another region called out, which is the yellow region on this slide. Strong sub-additivity tells you that the mutual information of I without is bigger than the mutual information of I with R. So now you have inequality that looks like this.
Sorry, Tom, can I ask
Yes.
a question here? Maybe I should have asked this a little bit earlier. So you're treating S-gen as if it's like a von Neumann quantum entropy. It's a fine-grained entropy. You're writing strong sub-additivity for it.
Well,
But
I haven't applied strong sub-additivity to S-gen. I've applied it to the mutual information of the quantum fields. So this is just a quantum field theory quantity that's obeying ordinary quantum field theory mutual strong sub-additivity.
I see. Okay. I see. Thanks.
Okay, so once you've reorganized things in this way, the quantity that's now appearing in this inequality is actually something that appears in the literature. This is what's called the mutual information regulator of entanglement entropy, introduced by Cassini, Huerta, Myers, and Yale. So they showed that the mutual information of a region with its complement is twice the finite part of the entanglement entropy, up to some subleading corrections. And now we can just subtract S finite from both sides of this, and we have an inequality. So we've derived the following inequality. It says that the finite part of the von Neumann entropy, plus these correction terms, which you can calculate following the methods of Cassini and collaborators, is greater than the finite normalized area of region I. So we've given a precise UV finite version of the Beckenstein area bound and proved that it must be violated in order to get an island.
Sorry, can you just quickly comment on what you mean by S finite? What is it? What is S finite?
S finite here is, well, one way of saying it is defined by this expression in the limit where out and I come close together. But what Cassini and collaborators showed is that this is equal to the finite part that we usually talk about, which is the one where you just subtract off the UV divergence.
So you're saying that this is the mutual information regulated entanglement entropy.
Exactly.
Thanks.
Yeah. So in our final Beckenstein bound, the way we should interpret this as a finite inequality is by saying that S finite here is the mutual information regulated piece of the entanglement entropy. Okay, so that was just to give you some flavor for where these inequalities come from. There's a similar, well, it uses some different elements, but a similar in spirit derivation of the other inequalities, which I'm not going to give in this talk. But now we can go out hunting for islands, knowing these general conditions. So now I'm going to turn in the last few minutes to the cosmology setup and apply what we've learned to that setting. The setup is the following. And I'll take plenty of time on this slide because this is sort of confusing. I want to make sure that this makes sense. So we're studying FRW universes. That's on the left. And our goal is to find islands in FRW. The one I've drawn here is recollapsing FRW, but we're also going to apply this to all the other FRWs. They're spatially flat FRWs. Okay, so in FRW, so this is the physical, think of the one on the left as the physical space-time, and we're interested in finding islands in that physical space-time. Now, since this is the FRW model, there's matter. This is not just geometry, there's matter in here, which is in a thermal state. So what we're going to do is purify that matter by introducing an auxiliary space-time. That's the one on the right. Okay, so we've introduced, so the physical space-time is FRW with matter in a thermal state. We've introduced an auxiliary Minkowski space with no gravity, but it has quantum field theory in it. And the quantum fields in this auxiliary space are entangled in a thermal field double state with our FRW, with the quantum fields in FRW. So we're introducing this auxiliary spacetime to purify the matter in FRW. And then we're going to ask, well, basically, we're going to treat this auxiliary spacetime like the Hawking radiation. So this non-gravitating auxiliary spacetime, we define a region R. That's like the radiation or rad region that we talked about in the black hole. And the question is whether if I have access to some region R in the auxiliary space, does that have an island in FRW? In other words, does that encode some of the physics of this cosmology?
Sorry, Tom, just
yes.
I'm a little bit confused about this picture. So this purification auxiliary Minkowski space in cosmology, what is it exactly? So you're imagining thermal fields in cosmology, but thermal fields in cosmology, they're not purified by something outside of the universe.
That's right, yeah. So, well, they may be, we don't know. The fields in cosmology, we usually imagine are just locally thermal. And, well, we don't know, but they could be locally thermal and globally pure. That is not the setup I'm in. I'm in a setup where we assume that the matter fields are literally thermal. They're in a mix, the matter fields in our cosmology are in a mixed state.
This is not an issue of them being entangled with something outside of a horizon or anything.
Well, I view it as a toy model for that. Okay, so this case is easier to work with, but I view it as a toy model for a case where the universe is in a pure state, but you have regions that are entangled. So like maybe, and I don't have a precise thing to map it onto, but what we have in mind is, for example, a situation where this universe came from some bubble, and this bubble nucleation is entangled with some matter elsewhere, and then we're going to ask whether there's islands inside our bubble. Something along those lines, but this is just a toy model for that.
That's fair, that's fair. Thanks.
Okay, so does this picture make sense? Are there any other questions about this?
Actually, sorry, let me bug you again about this. So one thing that I've been confused about is this issue of coarse grain versus fine grain entropy. For example, in this setup, I would have said that in cosmology, probably the thermal entropy we're talking about is some sort of a coarse grain entropy, right? But I guess you're saying that you should use these two notions in a sense interchangeably. Sometimes you could simplify your life by thinking that there is.
Well, if you want to find an island, I mean, I agree with that point of view, but you're not going to find an island if it's just a coarse-grained entropy. It really needs to be a fine-grained entropy, and that's because of this bound.
Yeah, this is what I was actually
right. The Beckenstein bound that we're trying to that we need to violate is not a coarse-grained Beckenstein bound. It's a fine-grained Beckenstein bound, and coarse-grained entropy is not going to cut it for trying to violate this and make an island appear. We really need the stuff in the potential island to be entangled with stuff that's somewhere else.
I see. Thank you.
Okay, so so that's the setup. And in this setup, there are two ways to look for islands. There's the hard way, where you pick a region I, pick a region R, you calculate the matter entropy of I union R. That's really hard to calculate. And then you look for extrema of the generalized entropy. That's a direct application of the island rule, the island formula to this setup. That turns out to be pretty hard, but there's an easy way, which is to apply the three conditions, which is just forget about region R and just look at the island itself and apply the three conditions to the region I. We're going to do this for spherically symmetric regions. And once you've done that, now these conditions are necessary. We haven't proved they're sufficient. So you're not quite done, but this tells you where to look. And once you know where to look, the direct calculation of the island is pretty easy. Okay, so this gives a much easier way of finding islands. These three conditions give you a much easier way of finding islands than the direct route. So finally, I can turn to the examples. The first example is a flat FRW universe with zero cosmological constant. So like a radiation dominated universe. It starts with a big bang and then expands forever. Let's apply the three conditions. The first condition says that the Beckenstein bound has to be violated. Now, that is certainly possible in the FRW cosmology. An easy way to see that, which was first noted by Fischler and Susskind, is that if you go back near the singularity of FRW, then the area term just goes to zero, whereas the co-moving matter entropy is constant and finite. The area term is going to zero. So certainly there's some region back here near the singularity where the Beckenstein area bound is violated. In fact, at any time in FRW, you can violate that bound just by taking your region to be large enough. So that's what this region is. This is the Beckenstein violating region. Then you can check the next condition, which says that the island has to be quantum normal. And you find a region like the blue region here. Well, these two regions don't overlap. So there cannot be islands in this model. And we're done. We're finished. There cannot possibly be islands. We never have to do directly do a calculation with the island rule. So this one doesn't have islands. Now here's one that does have islands. So this is an example of a flat FRW universe with a negative cosmological constant. In this case, the universe has a big bang, it expands, then it recollapses. Okay, so this is a universe that expands to a maximum size and recollapses. And the shaded regions here are the regions that satisfy the three conditions. So this region out here satisfies the Beckenstein bound condition. The blue region is the quantum normal condition, and the teardrop region is condition 3, the other quantum normal condition. And there's this region here, the triple overlap, where all three conditions are satisfied. And then you can look for islands in this triple overlap and prove that they really do exist. So the conclusion is that in a recollapsing universe, you do get islands. They're local. So basically what this picture is telling you is that the islands have to be large. They have to be large regions, and they have to be near the turnaround point in time. So these are large regions that exist near the point in time when the universe turns around, when the scale factor turns around and the universe starts to recollapse. So there are islands in this situation. But I think the interpretation of these islands is not so clear. The question that we'd really like to get at, and the question we'd really like to get at is something like Nima was sort of alluding to, which is something a little bit more realistic, where maybe you have eternal inflation with various bubbles forming, and then you can ask if islands actually show up in that physical inflationary scenario. We don't have examples like that in more than 2 dimensions. In 2 dimensions, if you have bubble nucleation, you do get islands, but in higher dimensions, it's very hard to do these calculations of the entropy, and I don't know the answer. I don't know whether bubble nucleation in higher dimensional inflation leads to this island effect or not. So I think that's one thing that would be really interesting to understand better. I had a couple comments on what are called Brockett wormholes, but I'm going to skip this. You can ask me about it later if you're interested, and jump right to the conclusion. So the conclusion: islands give us a way to apply methods of ADS-CFT beyond anti-de Sitter space. In particular, we can reach inside a black hole or a collapsing cosmology using entanglement. Entanglement was the key thing here. When we had the evaporating black hole, it was the entanglement of the radiation with the interior that allowed us to access the interior in this sort of pseudo-holographic way. There are a lot of questions that have not been answered. How does this dictionary work? How does the decoding work? What exactly does it mean for the state to be encoded in the radiation? What are the lessons for cosmology, for holography beyond anti-de Sitter? And finally, does this tell us anything about quantum cosmology and eternal inflation? I think that with these wormholes, we have to sort of revisit some of the ideas about things like the Hartle-Hawking wave function, the entropy of de Sitter space, the meaning of eternal inflation. And I think that'll be really interesting to revisit those and see whether these ideas from islands change any of the general wisdom about those topics. Okay, and I'll stop there. Thanks a lot.
Thank you so much, Tom, for the beautiful talk and very intriguing talk. So I'll start with a question. I'm sure there are plenty. So you were careful to just give an example of a negative cosmological constant. You have a verdict for positive cosmological constant, which is the cases that we are probably most interested in cosmology.
Yeah, the case of FRW, like pure FRW with a positive cosmological constant, is a lot like this one. The only difference is that the top line becomes horizontal instead of null. And again, there are no islands in that situation. Okay, so that rules out islands in the simplest possible version of like present day cosmology, which is where you just have like radiation dominated or matter dominated becoming CC, becoming positive CC dominated, like in the real world. But it doesn't rule out the possibility that there's something more complicated you could do, like with bubbles or eternal inflation, that could potentially have islands in the early universe.
Thank you so much. Are there any questions for Tom?
I wanna ask one thing. About the self-purification stuff, have you seen a finite quantum system model that that is analogous to this self-purification stuff?
Well, when you say self-purification, you're referring to this discussion of whether this is the more realistic version of entanglement in cosmology, I guess? What do you mean by self-purification?
Sorry, actually about the page card. So
I see. Right. You mean the fact that the island is naturally incorporated and then purifying. Well, I can give a simple tensor network analog, and it's easy to cook up it's easy to cook up a tensor network analog of this, and there you can see the same effect.
Oh, okay.
If you want me to show you a slide with a tensor network, if that would be useful, I can show you that slide, but it would take some time to really explain it properly. So it's maybe we should like do other questions first, or
okay.
Or I could just show you, if you know tensor networks, I could just show you the slide and maybe it'll make sense.
Okay.
Please.
I guess I know the basics. Yeah.
This is how I think about it. This is a very simple-minded. There are much more sophisticated ways of doing this involving quantum error correcting codes and all that kind of thing. This is my simple-minded way of thinking about the quantum state of an island. Okay. A here, sorry, this is an old slide. So A here is what I've been calling RAD, the radiation region.
Okay.
And the point is that you have some big tensor network for the state out here.
Mm-hmm.
And the island I is like one of the internal tensors on that big tensor network. That's kind of the sense in which it's encoded. So this is the sense in which the region I is encoded in the quantum state of the radiation region A.
Okay, is this I works like isometry because you have like three
Yeah, I works like an isometry here. That's right.
Okay, so what is G here?
G here you should think of as the piece of the black hole that's like not in the island. So the black hole splits into two pieces, the part that's the island and the part that's not. And then the outside the black hole splits into two pieces, the part that's in the radiation that I have not collected and the radiation that I have collected.
Okay.
So that's kind of the splitting here.
So are these, oh, this is states, so you have, okay. And this time dependent, like, so how is this size of I change? Like, how is this I changes?
Yeah, the amount of entanglement is changing as a function of time.
Yeah.
So the way I think about it is that like this link is growing in dimension.
Okay.
That's the link that links the island to the radiation. Whereas this link here represents the area of the black hole, and that's shrinking in time.
Okay.
So you have this network where this link is growing, this link is shrinking. And when this link becomes big enough, you effectively incorporate I into A.
I see. Okay.
Like eventually this link will just disappear. And I will just be this floating extra tensor on top of A. Okay,
I see. Do you know how this trade-off rate changes, or is this quantified?
How what you said?
The rate of trade-off. So like, so this area of black hole goes small, and then you get more and more connection between I and A. So there should be like that.
Well, that's the page curve. That's the page curve. So the shrinking of this link is that downward line on the page curve.
Okay.
The growth of this link is Hawking's calculation of the upward line on the page curve, and so when these cross, there's sort of a transition.
Oh, okay, I see. Okay, thank you.
I have a quick question. So you mentioned something about 2D models being in your cosmology discussion, that you said you can give us examples in 2D of these bubbles. What did you have in mind? Can you say just a few words, point me to a reference?
Sure. Yeah, we did this example in our paper. This is the paper from the summer with Edgar and Ikun. So the model is JT gravity in 2 dimensions, where you have a nucleation of a flat space bubble. So you start in DS2. You start in 2-dimensional de Sitter, and you nucleate a flat space bubble in DS2. Now, this de Sitter solution in JT gravity is really more. It's not so much like higher dimensional de Sitter. It's more like a higher dimensional black hole, because in this solution, there are both crunching and expanding regions on Scri+. And what happens is the crunching regions end up being encoded in the expanding regions. So it's similar to the black hole case, where you think of the crunching bubbles as, not bubbles, the crunching regions of de Sitter as being the inside of a black hole, and the bubbles or the expanding regions as being the outside. I
guess your point was that this is a very 2-dimensional feature that's not gonna be at work at higher dimensions.
Yeah, if you try to take that intuition and lift it up to higher dimensions, you end up with a statement about de Sitter black holes, not a statement like the Nari black hole or something. You don't end up with a statement, or the Schwarzschild de Sitter. You don't end up with a statement about, or it doesn't naturally lift to a statement about bubbles at higher dimensional de Sitter. So it seems harder to do that case, and it's just been difficult to calculate.
Thanks. Are there any other questions? I asked too many myself. Any questions? If not, let me just ask one last question before we let you go, if you don't mind. So
sounds good.
You mentioned about this thing, you said that we don't know Hamiltonian in the context of the black hole and the page curve. you said that we don't know Hamiltonian evolution and S matrix and all that, but do you have reasons to think that there are simple arguments that there shouldn't be an S matrix? Like, for example, why can't you have various sectors with various number of islands and some amplitude to go from one sector to another sector? I guess I didn't really understand what you meant by there is no S matrix.
Well, for example, if I make a black hole by colliding like two particles that I know what they colliding two protons, I don't know how to calculate the wave function of the Hawking radiation.
Sure, but I know, supposedly,
I know,
yeah.
But even in principle is what I mean. So we know how to calculate the entropy of the Hawking radiation. It's the Page curve, and you have a Euclidean method to calculate it. But we don't know, even in principle, how to calculate the wave function of the radiation. And I think that that's a problem in principle, because I think that the answer will depend on the UV completion.
That's right. Okay, yeah, you're saying that there's just no way to know from the infrared. Yeah.
That's just more than the low energy theory even knows about. I don't think we'll ever have a low energy formula for that. Maybe if we work hard enough, we'll have a string theory formula. But I guess the surprise is that the low energy theory does know enough to calculate the entropy. It just doesn't know enough to calculate the transition matrix.
I mean, it would have been too much if we knew about the transition matrix in a sense.
Right, that's totally unexpected. We don't expect to be able to do that.
Yeah. Well,
that's like the difference between.
Oh, sorry.
Sorry, that's like the difference between calculating the Beckenstein-Hawking entropy by the Euclidean path integral and calculating it by counting the microstates of d-branes. So
that's right.
It's parallel to that.
Thank you so much, Tom, for the wonderful talk. And yeah, thank you. If you don't mind, we're gonna post a video on YouTube.
Sounds good.
Hopefully soon we're gonna have you come visit Purdue in person once everything's all over.
Hope so.
All right, guys. Thanks, everyone.
Thank you.
All right.
Nice talk.
See you, everyone.
Bye.